Okay, so we, in the last lecture, started talking about some crazy different kinds of developments to extend Euler's method to consider what we call multi-step approaches instead. So that is, instead of just using the tangents at points to estimate where we step forward, we use different estimates and we kind of combine them together in order to do that. We saw that in midpoint method, which allowed us to kind of I don't know. I use the analogy of sending forward a guide, sending forward a scout to look ahead, see what the tangent ahead is going to be like, and use that as a guide to say what direction we should step in order to go in a better direction than just using the tangent at the starting point. But as a matter of fact, that's a really simple approach compared to some of the schemes that are out there. Look on the board behind me. We have what's going to be called the RK4 scheme. I also just lost the cushion on my chair, but that's okay. Where it's actually a four-step approach where we use different estimates at different locations and we take kind of a weighted combination of all of those different tangent slopes to get a step in the right direction. That's interesting. It's really useful, and we're going to detail the math behind that and basically how it works so that you can use it yourself when approximating the solutions to initial problems. So why don't we get started with that? After we get through that, I will also help to explore with you some of the ways that we might represent these techniques. Sorry, I'm at the wrong spot, so let's move up. Here, this is where we needed to go. So yeah, the midpoint method that we talked about in that last video is one of the simplest Runge-Kutta schemes. Again, the pronunciation is funny. It's like, if I pronounced it properly, it's probably like Runge-Kutta or something like that. But I don't know. People say Runge-Kutta, so I'm gonna just go with that, and you can say whatever you want. So as I said, it's a matter of considering weighted averages of different kinds of slopes found in the current interval that you're working on a particular time step. So if you're calculating all of these things, I mean, the result is that you have many more steps in your program because you're letting a computer do this most of the time. We're going to do one example by hand, but like in general, you're doing so many more calculations that it tends to be much more computationally intensive. But the error that you get as a result is so greatly reduced that it's actually kind of incredible. So we're going to detail one of the schemes that is pretty commonly used to get very good results despite being relatively simple. And I just want to make it clear there are all sorts of different kinds of these weighted averages of different kinds of slopes that you might consider using. And some of them might be more useful for certain differential equations with different functions that are involved than others. But there's some that are just pretty common, and I want to detail some of them here, and then go into ways to represent different schemes so that you can look at a simple representation of one of these schemes and be able to translate it right into your own set of weighted averages. So the one that we're going to talk about here is called RK4 for Runge-Kutta 4. And it's one that strikes a balance between simplicity and accuracy. It's a four-step scheme. So you thought midpoint method was a lot of calculation? Well, wait until you see this. What you do is that you start with a K1. K1 would step in the direction that Euler's method would usually step in. We don't take that as our next estimate, but we do take it as, right? I said sending forward somebody to kind of scout out ahead. And that person is going to go half a step ahead. So Ti plus a half H, half a step ahead. It's going to check the slope at that point. But we're not going to go in that direction either. That person's going to shout back and say, oh, the slope right here is this. And the person back at the start goes in that direction as a scout forward and checks out that slope that's right there. So see, it also goes half a step forward. The next scout, the next estimate is a half a step in time forward, and it takes the initial yi and then takes the a half of K2. So it goes halfway up how much we would go to get to the next time step. And then they shout back. They give an estimate of which way to go. And the last estimate we get, we send a fourth scout out ahead, and they go a full step forward in time along the direction that we get for K3. So essentially, we're doing this one step at a time, and in the end, our final amount that we go forward, isn't just the last estimate either. We kind of make it a democratic decision. We have 4 different reports of what the different tangent slopes are doing. And in the end, what I'm going to do is take a weighted combination of all 4 of them. So see that? We take 1/6 of the first one. So 1/6 of the one that I know based on the tangent that's right here at the current point on the graph of the solution to the IVP, the initial condition. I take 1/6 of that last estimate, the furthest one out, and I put a little bit more emphasis on the ones in the middle, 1/3 and 1/3. But I take into account all of those different estimates to produce one estimate of how much I should be going up at that step. So the final thing I do is take that weighted combination, add it to the previous y, and that gives me the new estimate in y. yi plus 1 is equal to yi plus this big old weighted combination. Crazy. But that's what the scheme is, and it tends to be quite accurate. A lot of steps that are involved, and I just want you to think in terms of, right, what this graph is doing. You can see this, right? Let me actually go back to just chatting here, and I'll point this out. So the 4 weighted combinations that are the 4 different pieces of this combination are right here. The first estimate is taken at whatever the initial condition was. I move forward half a step in time, and I look at what the tangent slope of the solution that would be passing through that curve there. It's probably something close to the true one, which I've got in the blue right here. I report that slope back here, the amount that I went up to get there. And I walk up that far. And my next estimate's going to be, well, in this drawing, it's going to be above the blue curve. And then there's going to be another solution that goes through there. That tangent slope I report back to the start, and I walk along that line, this time a full time step. I get one last estimate. This one happens to be below again. And in the end, I'm going to take 1/6 of the estimate that I got from that one, 1/6 of the estimate that I got from this one, and 1/3 of each of those middle 2. That creates a weighted average, and I use that weighted average to add together and get a final estimate as we go forward. That's what's happening here. That's tough. There are lots of steps to that. But I want to kind of translate that into, right, what the language is saying here. What is this math? You can look at this and see all this alphabetic soup, you know? K's and H's and F's and Y's and T's and all this kind of stuff everywhere. But that's what's happening. I'm getting different estimates, and at the end I'm combining them together into one democratic decision. All 4 of those people that shouted back to me, go this way, go that way, go this way, go that way. I'm like, you know what? I'm going to cut like kind of an average between all of you. I'm going to go this way. And that's what we use to get to the next estimate. So hopefully that makes some sense. Cool. And of course, this is one example. You can take all sorts of different combinations. And as I said, we're going to extend this to some different kinds of schemes that we can use. You can have that at every single step, maybe the first scout you send forward. Or the, like I'm saying, get an estimate here. The second one goes forward. And maybe the next one depends not just on K2, for example, but maybe it's a combination of all of the previous estimates. Maybe it's a combination of of the K2 and the K1. Maybe it's a combination of any of the previous estimates and so on. And different kinds of combinations might be useful for different sorts of situations and different differential equations. So there are tons of papers out there on which estimate might be useful in which situation, and some of the precise combinations are really very precise and very intricate. So my job isn't to go through every single possibility that's there. What we're going to do is understand this one, and then extend to some notation that will let you understand all sorts of different kinds of schemes as they come up. So hopefully this is an okay start. It's hard to talk about because there are a lot of different pieces here. We're going to work on a different initial value problem than we've had. we're going to work on y prime equals t ln y. So this is my f. This is f of t and y right here. My initial conditions here say that t0 equals 0 and y0 equals 2. And we're using the RK4 scheme to estimate the value of the solution at t equals 1 using a step size of 1. Step size of 1 means h equals 1. So we're going to do one iteration because I started at t equals 0. I need to get an estimate at t equals 1. So we need just one step forward, which is fine because we have lots of calculations to do. Using h equals 1 right there. That's what the step size is, okay? And let's get started here. We have all the information we need. Let's write down that scheme so we remember what it is and we're familiar with using it. It was K1 equals, let me just make sure that I have it down right. H times f of yi, f of ti yi, sorry. The second estimate, K2, is h times, and it is f of ti plus 1/2 h, so half a step forward in time, and then we use yi plus 1/2 K1. So we're going up half the distance that we would have gotten if we just taken that first piece of advice, if you will. The next one, though, is half a step forward in time, except using K2 and going half the distance up that way. And then the last piece is h times f of ti plus a full time step forward and yi plus the full thing of K3. And then we use r equals 1/6 of K1 plus 1/3 of K2 plus 1/3 of K3 plus 1/6 of K4. So that's what we're using. This here is the scheme. And at the end of the day, once you calculate r, that's the amount that we tack on to the old y to get to the new one. So yi plus 1 equals yi plus r. So that's it. Let's do it. We just have to do one iteration, so we have to get through it. But we're going to start here with t0 equals 0, y0 equals 2. We have those four quantities to calculate, and the first one is k1. So k1 equals h was 1, and then we need f of t0, y0. So that's 0 and 2. So that's not hard. I can take this, I can plug it into the function, and if we do, we end up with 1 times t would be 0 and ln 2. So we get 0. So k1 is 0. All right, simple enough. We'll take it. K2 will be 1 times, and let's think about this. It's going to be f of, I need the initial time plus a half step forward. So this is going to be 0.5 because my step size is 1. Then I'm going to take y0. Oh, whoops. Let's just get rid of this. We're going to take the y0 and we're going to add half of the previous estimate. Well, y0 was 2, and we're going to add half of 0, which is the previous estimate. So this is what we end up with, 0.5 and 2. So just as a reminder here, this 2 came from 2 plus 1/2 of the previous, the k1, that's 0. So that's just what this 2 is. But this time, if you plug in, we're going to get, the h was 1, so that's fine. T this time is 0.5. And we have ln 2. And if you work this out, we get about 0. To 4 decimal places. I did 3.466. Okay. That's the second. We're going to go back, and we're going to use that in K3. So K3 is 1 times f of half a step forward, and it's going to be 2 plus a half of what we just wrote down. So I think that's going to be 2.1733. That's not magic. That's me using the formula, right? This is 2 plus 1/2 of the estimate we just did. 0.3466. That's me going half a step along that line, stopping and getting the tangent line there. That's what I'm doing. Okay. So this is going to give me 1. I keep writing the 1, but I know I don't need to, but I want you to see it in the formula, right? 0.5 ln of a 2.1733. This works out to, if you do the math, 0.3881. And that's not enough. We need to use that to find a fourth estimate. So K4 is going to equal 1 times f of, this time we take a full step forward, 1. We take 2.3881, and that is to take our 2, and we're adding the full of K3. So that's what our scheme said. That's what we're going to do. It's 0.3881. So this is the quantity that we're using. And we're going to get here 1 times the ln of 2.3881, which is going to give us, that works out to 0.8705. So we've got our 4K values. There's 0, there's 0.3466, there's 0.3881, there's 0.8705. And I want you to think of those like 4 people yelling at you which way to go. And you're going to sort of try to listen to all of them in different ways, and you're going to concentrate on the ones in the middle, but you're going to give everybody some emphasis. The R is going to be given by 1/6 of the first, plus 1/3 of the second, plus 1/3 of the third, plus 1/6 of the fourth. And if you work all of that out, I'm just putting all of those values in, this should calculate to about 0.3890. So it happens that third estimate was really close to what we're going to go with in this scheme. But that's just what it turns out to be. Thus, y1 is going to, so our next estimate for y, like one step in the future, our best estimate that we can get using this scheme is 2, the old y, plus that r. So 2.3890, like that. Crazy, eh? However, it turns out that a lot of the time, for a wide variety of differential equations, this does very, very well. I actually don't have the solution on hand, but you could check it for yourself if you had an online calculator or whatever. So that's how it works. I hope it makes sense. I know there are a lot of steps that are involved, but I think that if you think in terms of this, like, you're just taking a different, you're getting information, you're getting different information from different points in this solution space, and you're using that to kind of inform the best possible approach forward. I think it will become clear why this could be more powerful. Okay, so let's think for a second. There's so many, really an infinite number of possibilities for different Runge-Kutta combinations. RK4 is just one of them, okay? And I want you to take note of that, because, right, like, given a scheme where I'm producing different estimates using different combinations of previous estimates, like, you should be able to take that and understand what we just did, and based on a slightly different graph, a different chart, be able to produce a different sort of estimate. And for certain combinations, you might get better estimates than others. But it's really useful, instead of having to memorize one scheme or whatever, if I can represent a scheme in a compact way that carries all the information from that scheme, that seems like it would be really convenient. And it's also really convenient when it comes to coding, which I'm going to save for the next video. But we can do this using something that's called a Butcher Tableau. And you're going to get this down so you don't butcher the Butcher Tableaus. That was the cheapest joke ever, but I have to get my puns in where I can, my dad jokes. Here's what a Butcher Tableau looks like. Okay, so this is what it is. We have this, like, this cross hatch sort of thing that sections things off. And let's read it. Let's try to see what we see here. We see a 0, 1/2, 1/2, 1. And that looks really familiar, right? Those sound like our time steps forward. We see 4 rows for 4 time steps, so that makes some sense. but the first one involves no going in forward in time to get an estimate. The middle two are taking half a step forward in time to get the next estimate, and the last one. So I think that makes some sense. We can see maybe where those come from. 1/2. Those describe the pieces that were attached to the y's, right? Like we had y0 in the top one. Let me go back in time so you can see the scheme, right? yi without anything added whatsoever. The second one we had yi plus a half k1. This third one we had yi plus a half k2. The last one we had yi plus k3. See the coefficients? 0, 1/2, 1/2, 1. In front of any previous k values. Well, let's go back to that tableau, and you can see that right here. There's nothing in the top row. That will typically be the case. 1/2, 1/2, 1. Due to the dependence on the different kinds of estimates that we've got. There's zeros here because of the fact that the third and the fourth estimates don't ever rely on K1 or on K2. They only ever rely on the one before it. Okay? This last row, think about where you've seen those coefficients. 1/6, 1/3, 1/3, 1/6. Those refer to the final combination of all four of those k values that we found. When it's arranged like this, it can well define and establish one of these methods, one of these Runge-Kutta methods. And this is the one for RK4 because I can relate it to that scheme that we just did. So that's a lot to remember. It's a lot to take in, and I understand that. In fact, before I started teaching this course, I'd never seen this before either. But I found this was a very, very useful thing to know. It was more powerful than anything else. So I had to learn it. And then I was like, God, this is confusing. I need a better way to convey this to students. And so I came up with this. I don't know if it's helpful. But there's a little chart here. So this here is going to go through the very same thing that I described, but put it in kind of a graphical form. So I have here in this top bubble, this step evaluates f at t equals ti plus question mark h, where this value is the question mark. And see, 0, 1/2 h, 1/2 h, 1. So you can see those for yourself. The dependence of each step on k1, k2, k3, k4, right? This is what this is talking about. There's no dependence on any of them in that first step, but the second one does depend on a half k1. The third one does depend on a half k2. The last one depends on 1 k3. But it's possible that I could take a combination of different previous steps for that last step. It's possible that I could take a combination of previous steps for this one. So it might not be 0 and a half. Maybe it's 1/4 and 1/4. Something like that. It's like taking a weighted combination of all of the information you've got so far to try and inform where you go next. Yeah, and so I kind of tried to outline that right here. And finally, the final weighting of the 4k values used to make R go across this way. And the idea is that we can combine it using that weighted average to give you the R, which tells you how much we have to add to Y to get the next estimate. So I think that this is a handy little table that you can refer to that might hopefully bring back some of the some of this conversation when you're working on this on your own, because it is pretty tough. But let's take this and see if we can do some work on our own. So I have a couple of examples set up here. Consider the Butcher Tableau given by this. So this is looking like a 3-step scheme because I have 1, 2, 3 rows above. The final R value is given by that bottom row. And a really good example would be write down the Runge-Kutta method that is represented in this Butcher Tableau. So here we would take K1 equals H and then F of Ti, Yi. No dependence, no stepping forward in time. So Ti plus 0H, nothing like that. And Y doesn't depend on any previous steps because there are no previous steps. That takes care of this top row. The second one is going to be a step forward in time. So ti, how much in time? Well, it looks like half a step forward in time. So 1/2 h. And then we're going to have yi plus, and then it looks like it's going to be 1/2 the estimate before. So 1/2 k1, like that. That takes care of this row. That's the second step, and we go on to the third. The third step is going to be a full step forward in time. So hf of ti plus a full h, a full step, and then we have yi plus 1/4 k1 plus 3/4 k2. So this is taking like a weighted combination of both of the previous estimates to get the next estimate. Okay, so it's going to be 1/4 k1 plus 3/4 k2, just like that. The final weighted average takes into account all three of those, and in this case, it looks like it would be a 1/5 k1 plus 3/5 k2 plus 1/5 k3. And this would be our scheme. You would then take this r and add it to your old y to get the new y. Okay? So hopefully that makes some sense. Seeing that extra example might really help to kind of help the knowledge kind of settle in your brain a little bit. There's a little caveat I want to mention here. To make sure that when I'm walking forward, I land on that line segment and I'm sampling the right spot, I need to make sure this Butcher Tableau is consistent. And that means that whatever this number is here, whatever number this is here, all the numbers on the other side have to add to that number, right? If I go halfway up the line, I need to be halfway up the y to make sure that I'm getting the right height. So they go like over and up and land on that line segment that the tangent line is pointing on. If I am going over one, I need a weighted average in order to make sure that I land in the right place. Okay, so that's the important thing. I need to make sure that the Tableau is consistent or else the scheme doesn't work. Okay, so that would ensure that we have a chance of approximating the initial value problem solution. I'm just looking at my words right here. It says, that is to ensure that the values produced by the corresponding team, this is the wrong word, but the corresponding, I want to say this should probably be like estimate or something like that. Just forget this word for now. Well, I'll fix that later. So we require that on each row, all values on the right add up to the value on the left. And similarly, on the bottom row, since I need a weighted combination of all of the estimates, I definitely need to make sure that the bottom row always adds up to 1, right? It's like if you take an average of two things, you need a half of the first plus a half of the second. A half plus a half is a 1. If I want to take an average of three things, I'm going to add up a third of the first, a third of the second, a third of the third, right? The weighted, like all of those coefficients have to add up to 1. Or I'm not taking an average, I'm doing something else. I'm taking some other weird combination. So that's really important as well. Okay, we have one last example here just to see how another method works, and it relates back to some old material. The midpoint method, going back to the last lesson that we did, was a two-step method. And doesn't that seem so easy now? We have that the first estimate was produced by h f of ti yi, and the second estimate was h times, and then we go half a step forward, and we take half of the k1, the previous estimate. Yi plus 1 was given by the second estimate alone added to your yi. So if we wanted to write this as a Butcher Tableau, two-step scheme, the first one, let's just remind ourselves of how this works. The first one's going to have a 0 because there's no dependence on any steps forward in time or on previous estimates and stuff like that. There's going to be a 0 up here. The second step is going to be a half a step forward in time, so we're going to put a 1/2 here. There is dependence on K1 with a 1/2 right there. And then our final estimate is going to be given by, let's see, nothing here because there's no, right? This here would be our R, right? I'm adding the R to the previous estimate, and the R is just completely 100% K2. So there's 0 dependence on K1 in the final weighted average, and 1 dependence on K2. And so this is what it looks like. So it looks really simple compared to what we've done before, but that makes sense because we only have 2 steps in this method. But I think you can see the power here, because then I can draw this chart and it's a hell of a lot simpler in its structure, in its form, a lot less to write down, but it carries all of the information of what we had in that scheme before. So that's where we're at. And hopefully I was able to boil this down. I think it's tough stuff, you know? I think it's not easy. And if you found that some of these explanations were helpful, if you liked the board, if you liked talking about the tableaus, if you liked the examples and so on, I'd be glad to hear from you to see, like, am I doing this justice? Am I doing a good enough job explaining how these things come together? Because it's hard, right? When you're juggling so many different quantities, when you're trying to, like, take the idea of weighting a bunch of different estimates and producing one new estimate and going forward, that's a hard enough concept in itself without trying to make math out of it at the same time, you know? So, hopefully it went okay. Email me if you don't think it went okay, or if you want some clarifications and stuff. I'm always happy to help. So yeah, the next lecture that we talk about is going to be about coding these darn things. It's going to be pretty involved, but you can just imagine that where you have a Butcher Tableau, you can translate that really well into a matrix representation. And so we'll talk a little bit about that, and yeah, round out the end of this section of the notes. So until then, I bid you all a fond farewell, and see you soon.